observed discharge is going up, so that is also going up simulation. I mean, the pattern is matching well, but the values are not so coincidental. So that should be matched. How we can do? So that is the two way two way you can achieve that. The first way is go back to the each and every subbasins, okay, and then change the loss parameters and the transform parameters. This is the one way, and this is what we call it as a manual calibration. But you might see, you can see that I mean, in this there are like 11 to 12 subbasins are there. Changing each and the small values and making the combination, it might lead to the 10,000 or more than 10,000 simulations, right? Because first time I will change at one subbasin certain values, and then I'll keep others constant, right? I like global sensitivity, so I'll go on doing all these things, and I will come to the point where the model might be giving good accuracy, means the maximum accuracy what we can achieve. But that is highly laborious, and no one expects to do that way. I mean, if you are achieving certainly good accuracy, then in that case it will be okay. But we have an option called auto calibration options, and those comes up with a very good algorithms, which whatever I was talking, that way they does that computations, and then they stores the simulations, and finally they gives the final best simulations. So I just want to glance you, I'll take you through a simple procedure, how exactly it is happening in the system, like in the HEC-HMS. So first of all, you must know that what is Monte Carlo method, because basically many of the calibration techniques depends on Monte Carlo method. Monte Carlo method in turn depends on central limit theorem. What does the central limit theorem says? Let's say you have certain values, right? Certain values means, suppose you are having a series called, suppose you say a series saying 1, 2 and 3, likewise it will go up and it will come to around 500. So means all these values are randomly arranged. I just wrote like this, but all the values are randomly arranged. Suppose for this, for all these data, I group into a small grids. Like, anyone has any question? Okay, no questions. Suppose if I make it in a groups, like suppose if I say the interval is 2, like any data it is, so I say just 2 is the interval. If the 2 is the interval, then 1 and 2 will come in one group. So the 2 is very small, so in that case we'll take 10. Okay, so if you take the 10, means between 1 to 10 data magnitude, how many data are coming? Likewise, I can plot a histogram, right? Suppose 1 to 10, there were like some certain values were there. After that, there were certain again values were there. I mean, within next 10 to 20 range, again 20 to 30 range, there were some more values were there. Likewise, again it will come up. So if that is the case, then you might see I had just drawn very like a symmetrical diagram, symmetrical histogram. Like almost 50% data are coming this left side and 50% data are distributed towards right side. But this case may not be true in real sense. Why? Because many of the data are either left skewed or right skewed, like this. Left skewed or right skewed. Or some data can also be like this. So in this case, how can you split your parameter values will be a big question, right? As I was saying, like you have to change small values. You have to put those values and simulate it and then run it, and then you store the values for whichever simulation the best efficiency you are getting. So efficiency means like R square value is near to 1 or RMS is near to 0. Likewise, best efficiency you are getting. So that will be said or called as a best simulation. So suppose a certain parameter varies like this. In that case, what will happen is, again, we have to divide this small data. Okay, you have to divide, because we are dividing intervals, no, or giving the inputs. Like maybe as small interval it is, the more accurate you will get, or more good results you will get. So the small interval will divide. What limit theorem says? What this theorem says is, suppose you divide and you increase the number of samples. Like if you already it was 10, you make it small fragments in this data, divide in small fragments. Then how this will lead to? This will lead to a bell-shaped curve. This is what the statement of the central limit theorem is. Okay, so based on the central limit theorem, what we can do is we can simulate those parameters. I mean, those generate the values of the parameters, and then we can have the understanding or calibration of the models. So after central limit theorem, mainly what people do is we go for a sampling, like so complete probability distribution based on sampling. Then what we do is we create samples, we divide those samples, like suppose suction head is varying between 10 to 50. So what I will do is, within 10 to 50 I will divide with the interval of 0.5. So 10, 10.5, 11, 11.5. Likewise I will go up to 50. Likewise I will divide everything, and then I'll store that particular parameter. Likewise I have to combine for all the parameters of this particular subbasin, and then as likewise for all the subbasins. Suppose there are 4 parameters of particular basins, and suppose there is a 10 subbasins. So it will be total 40 parameters values will be there. So likewise again you are dividing in, suppose at interval of 10, suppose 0.5 or whatsoever, and the number is 10,000. So 40 into 10,000. So total 40 into 10,000 will be the number of simulations you have to carry out just to calibrate the model, right? So that's why it's manually it is too difficult. So sometimes what we do is we come to the certain approximations where these values and these accuracies are okay for me, so I will move ahead, and that's the satisfactory model for me. So likewise this will be very tedious task. So many of the times we don't prefer that way. So then how it is done is like, so whatever the parameters are there, suppose parameter value is, suppose certain central value of the parameter is suppose 10, then we take upstream like plus 50% added to the like left side, and plus 50% added to the right side. Means we keeping the range of the value like mid range of the given value. We completely divide into the upper boundary and lower boundary as if it is like a distributing like a bell-shaped curves. So likewise, which again we generate samples, and then whatever the samples we generated, what we do is we decide a certain objective functions. Objective function means, suppose whatever the parameter set combination I have defined, those combination parameters should go into the HEC-RAS model, and then those values should be changed, and those change values should simulate the runoff, and then that should be compared with your observed runoff, and that should store the efficiency also. After having all the simulations, I'll see which simulation has the least error. If suppose my objective function is error, or NSC value if it is 1, so I will check out whichever the simulation has near to 1 value it has given, that will be your best simulation, right? So this whole mathematics is happening in the HEC-RAS, where likewise. So I hope everyone has done these simulations. If it is done, I mean, if it is simulated, then please say yes in your chat box. How many of you are ready with this model? Can anybody say yes? Because we are more than 150 people here. So many people can say yes in a single second. Okay, fine. So everyone has opened that HEC-RAS. Does anybody has the problem in opening this model which I have sent you earlier? Thank you, I got it. You all have opened your models. I understood. So okay, so and does anyone has an issue in opening the model which I have sent? I mean, that should be the least problem, because when you are understood the whole modeling, then opening should not be a big issue. But still, I'm asking this question if anybody has not followed it. I presume everyone has opened this model. Okay, fine. So once if you open it, then you see here this I'm pointing at this point. Okay, this one is the components. Compute means whichever number of simulation or whatever number of simulation I have done, all the simulations will be stored here, and all those particular parameter simulation you can check out from here also. If you can double click on this, so whatever the parameters were given there, that parameter values you can simulate here. So earlier we did 33rd simulation, so I can just say it. I can just double click this and then run from here. So it will again directly compute all the parameter values. So if it comes 100%, means there is no error in that. Okay, so then I'll check it out once again from by clicking on this junction, because there where that is my outlet, and I'm checking the this is where point. This is the point where I have given the observed discharge also using cause. We can see here options, and in observed flow I have given the discharge value. So now what I will do is I'll check out what is the simulation. So simulation is quite good, but still it can be improved. Okay, so then I can check out from here. I can still check out what is the percentage bias, RMS and everything. So when I say summary results, suppose if beside to that there is a summary result, okay, at the junction. So I can just say what is the error. So RMSA standard deviation is 0.7%, bias is 40.6, Nash coefficient is 0.488, means it is quite a poor model, right? We can and the time of discharge, you can see here it is 3rd August 2013. 3rd August 2013. So this model has still scope to improve. What I will do is I'll just go to the compute, then in the parameter, in the components. Okay, just a second. Okay, somebody's texting. Project version 4 is not compatible with HEC-RAS version. Project, no, just say yes. When you are not, when it asks for the not, it can't say like that. It will say, it will ask you when you just say yes, whenever you ask this question, when you get an error, so you will directly get an completely open folder file. Okay, it might issue an error because that model was created long back, so it might be giving an error, but that should not be a problem. You just open it. Whenever there's some dialog box on, just say yes, it will open it. Okay, automatically that version, this version will convert to that version. No issues. Okay, okay. Okay, so once if you do this, then what you have to do is go to compute. Okay, then create, then I'll say optimization trial. This optimization trial is for your model calibration. So I'll say calibration 1. Okay, and then I'll say just next, then say next, and then say just finish. So now you must see your calibration 1 optimization. These are earlier calibrations. So this calibration 1 is now added. Okay. Now, if this is the calibration, then I must say like what all the subbasins parameters should be optimized. Okay. And then the time also you have to give the basin is the same. This should be same as your simulation time. I hope somebody has. Hence, it is not possible to work for higher to lower version. And file which provided by Rathod sir is for 4.7. I think you are working on HEC-RAS 4.5. And the file which is provided Rathod sir is for. Okay, so it's a conversation from the. No, whatsoever the I'm see, I am using the same file I have opened, whichever I have sent you. Okay, and that should not give a problem. Even if it is giving problem, I don't know. You just install the latest version of HEC-RAS. That should be a solution for that. I mean, there is no issue in connection. Apart from this,
Praveen sir, you go ahead. Actually, it should be open in the latest version which we have forwarded to the participant. Okay, so it is working actually. Okay.
Okay, fine. So it is working. I can confirm that it's working with some others also. So that should not be an issue. Okay, so this uncertainty part is very much important. So, and there we have added in the compute, we just created an optimization trials. We just added the optimization trial. Okay. So once you add, I just say calibration, add rename returns in next, then this part will come in optimization, in compute, in optimization trials, I have added calibration. But here I should mention the timing also. What time what is the simulation time? So in this case, what is the time? I just should know the timing. So I'll just note down from here. Better always refer, don't refer and there, just refer, go to time series, and any gauging stations you go, there you have the timing. So I'll just note down the timing. It's like 01 August 2013 at 8:05 August 2013 at 8. Okay. I'll come to compute, I'll come to calibration, and I'll put this date 01 August 2013, and timing is 08:00 05 August 2013, and it should, when timing should be 08:00. Okay, so this we have added. So maximum iterations, like per iterations, maximum iteration you can keep it as like 1,000 or whatsoever, and then a tolerance should be like whatever. Suppose optimization trials, what I'm saying is, in objective, my objective function is minimization goal. What I'm trying to minimize, I minimize at the location causeway, means causeway is the junction. So I'm minimizing the statistics should be RMSE, root mean square error. See here, we can change root, time series discharge, causeway, and minimization problem it is. And basin 1, meteorologic 1 it is, time is, everything is done. Okay, now I have to add some parameters, right? This is just a trial, what all trials in general trial what I want to make, but what exactly I'm trying to make, that should also reflect in this. Before that, I just want to check once here. 6700. Okay, fine. Okay, I'll just keep this 00. Sometimes you get an error saying like your time series exceeding the given value. So I'll just keep it as minimal as possible, close to the last value. This value should be close to the last value, and this should be just next to your first value. Then you won't get an error saying either the exceeding the values or the least, like you are not covering under the range before starting. Once your simulation starts before your actual time series, so that error might get some time. So that's why in advanced I'm taking a precaution saying like just I'm giving an extra time, like starting next hour, next time series from the top, and the second last times value from the bottom. That value I'm giving. Okay. So if you understood this, then let's go with the parameters. I'll add parameters. See, one parameter added. Now it will ask which parameter you want to add. I'll just say Amli, means this is station. Okay. In the Amli, which parameter you want to, it is asking which parameter you want to optimize. I'll just say conductivity. Okay. So it will automatically take what all the conductivity parameters are there. So it will take, we have given value is 0.4, and this is divided from minus 0.0001 to 250. Okay. So likewise, again, I have to add some more parameters. At least 2 parameters should be there. You can add as much as parameters for as much as your bases of basins. So in that case, you'll say saturated content. So this is the value it took. It will automatically decide minimum. If at all you have, if suppose you want to minimize the effort of the this algorithm, you can reduce these parameters. Suppose 0.35 is the close value. You know that it cannot be less than 0.2 and cannot be more than 0.4. So you can reduce this range so that the computation effort will be less by the algorithm. Okay. So again, you can add the parameters. I just say I'll add the parameter after promptly. I'll just say Mangrove and just say conductivity. So likewise, So just likewise, you can add all the parameters, as much as parameters you want to. And technically, you should add almost all the parameters, but it should not be like so much. Like otherwise, it will take so much time. But that should not be an issue, right? So when you have a lot of time, so you can add all the parameters and you can simulate. Okay, so I am just adding 4 parameters for the demonstration. Okay. Okay. So then, so once if you do, then just say compute. You can directly from here, you can say compute. So it is giving some error, it seems. Check it out. Okay, so minimum value is below 0. As I was saying, so there is some issue with the values. So we can modify those values. Minimum value limit means Greenland parameters, conductivity, Amli, Mongrel, and there's a problem with the conductivity issue. Okay, we'll check it out. I will go to the conductivity. So this one, green amped, minimum is 0.4. I'll just say here, I'll change this one to 0.1. So conductivity Amli is, we are solved the issue. Conductivity at Mongrel. I'll go to Mongrel, and the conductivity is, I'll just say 0.1. And then suction. What it says is minimum value is below limit 1 for the parameter. So I'll just say green amped Kakrapper. Kakrapper, green amped. Okay, suction head. Okay. Section is 5. Okay. I'll just say 50. I can just, I mean, that value sense I should have, like what parameter I'm giving. So based on that soil table and the table what I shown in earlier in the presentation, that sense I should have it, right? This, like whatever I'm just giving section head, I'm just giving random values, but that should not be there. So I should have sense what I'm giving, but right now it's so fine. We can just compute. So now it is simulating. Did anyone encountered with the same error what I got? Can we optimize CA number of particular subbasin with optimization trial? Of course, you can optimize any parameters of any subbasins. So it's just a free hand. I'll just show you once again with the this thing, but sometimes it takes a lot of time. That's an issue. So sir, can you please repeat the calibration process? I'll definitely repeat. Your organizer had given me 30 minutes. If they permit, then I will extend this for next 15 minutes.
Yes, you can take.
Okay, sir. Thank you for permitting. I'll once again follow the entire procedure for calibration, because this is the most important. Anybody can develop a model, but calibration, I mean, if you understood the whole process, how to do it, then it hardly takes 10 to 15 minutes to develop a model. But later on, calibration requires your skills, your understanding, your sense of the parameters, and of course, experience. Okay. Multi-site. I shown, you know, it. Dheeraj sir, as I was showing you here, and even in fact error also what error I have got was for the multi-site only. Suppose multi-site means, suppose this is at sub-basin 1 and this is at sub-basin somewhere else, like Kakrapar. So this is like different sub-basin only. So of course you can go for multi-site calibration at a particular, and that is a good idea actually, because At one point we move from the individual points, it will be again complicated process. So what you do is you put all the sites, whichever parameter you think it is important, and then you do it. So I'll just show you this thing, parameter one. Because I had chosen the this thing, I had chosen the green amp model, so SES curve number is not coming in this. Suppose I had chosen something else. Suppose I'll show you one thing. Okay, again I'm making some modification in the model, and then I'll show you what exactly how we can do that. As sir Dr. Desai sir has asked the question about multi-site calibration. I'll show you one more time. Let's come to AMLI. Okay, here we will change let's say AMLI. Here we will change green and SES curve number. Okay, loss method I'll just say AMLI SES curve number. I'll just say S. The moment I need change loss method SES curve number, loss method I have to define curve number. I'll just in randomly I'll just say 80, and then I'll just say 0.05 is my percentage imperviousness. Okay, once if I do this again, I have to simulate that. Okay, so everything will remain same. I'll go to compute and simulation run manager. I can just simulate from here itself, or else I have to create that way. Simulation, I'll just say 35. Okay, I'll just say again CN. This is the CN change simulation. Fine. I hope everyone is understanding this one. Next, I'll just say next, finish. If that is done, then I'll come here. Simulation change with CN. I have changed at AMLI. I have changed loss number. I have changed loss method as CN curve number, and then I have simulated it. Again, I will run it. Okay, it has ran now. Okay. Now what I will do is I'll come back to compute. I'll just in this calibration process itself, in second parameter, I'll just say AMLI. I guess I'll just say SES curve number I will define, and then I guess here also earlier AMLI, and parameter will be initial abstraction, and I'll just say SES unit of lag time, and I'll just say it is like 10 minutes. Okay. AMLI and this I'll just say lag time is this one at this parameter, and in here I'll just optimize the curve number, and then these are the variations. Okay, before that I just wanted to show you the results, right? So I have not computed this one. I've changed the parameters, but let's keep as it is. We'll come to results. Whatever optimization I have done, I have to see here also. Okay, so this was the results of the calibration one, what we did earlier. I can just see here optimization function summary. So what actually I'm getting error or everything that I can see. So percentage difference is 7.9 in the peak value. Parameter optimized, whatever the parameters were there, how they optimized, that I can see from here. Just see earlier it is 0.4, now it changed to optimized value is 3.4 to get best simulation. So 0.4, 1.7, 250, it is somewhere changed to green abstraction is too high. Sometimes you might get illogical values also. You will end up with illogical values also. How to constrain those values? By defining the maximum value cannot exceed something like that sense. Suppose this parameter is there. So in this case, maximum minutes cannot be more than 30,000, right? 30,000. So I can limit this one to around 500 minutes. So that maximum value cannot exceed, so that other parameters will get influenced and that parameter get optimized. So likewise, how we can see the values what we have optimized. Now what we will do is, okay. Now again I will compute. As I change these parameters, like at AMLI I changed SES curve number as a loss method. That's why I changed lag time as one of the optimizing parameter, and AMLI itself as a curve number, just to demonstrate that. So I'll just say compute. So I hope everyone is understanding it. If at all you are understanding it, then just say yes in chat box. Of course, you are more than 100. I should get yes within like short seconds, around hundreds. Quick, say yes. I hope everyone is understanding what exactly I want to demonstrate, right? Calibration. So this is how you do the calibration in HEC-HMS. It's a very simple model, but if at all you want to do the simulations of different variety, or you want to carry out some different research also, you can carry out. Still in 2020s, 21, also you are getting so many papers are getting published using HEC-HMS. Though SWOT is very good model, though, but it requires a lot of parameters. Within less parameters, you want to study some effect or some impacts. In that case, you can use this HEC-HMS and you can study all the impacts or everything. So in that case, simple yet effective model you can simulate. Suppose sometimes such a huge model is not required for a simple simulations. In that case, if at all you develop certain simple models like maybe empirical models, you can compare all those empirical models with existing empirical models in HEC-HMS, and you can prove your theory like how perfect it is for certain area, right? So many SCS CN curves which methods are developed maybe for the foreign countries, right? For your countries or for particularly your area, you want to optimize or you want to develop certain new technique for the computation of unit hydrograph, or maybe the runoff technique modeling. So you can develop your own model for computation of runoff, and then you compare here also. That way you can do. Okay, so once if simulation is over, I'll just come to results. Then okay, calib only. I'll check it out summary. Earlier it was 7.9. Now also it's showing same value. And just say observe data. Can you see here how it is? Like earlier it is like this. Okay. Now if you see, okay. Our optimization has changed this value. Observed value became more earlier. In actual simulations, the values were under predicted, but here after optimization, the values are got somewhat over predicted. So you go on try with different parameters. You can optimize everything with certain good accuracy. So sometimes even this accuracy will be sometimes this accuracy also okay for me. So I just say I mean that is fine like that. So again, it depends on what is the acceptance criteria. Likewise, you have to see. So optimize parameters if you want to see, like here curve number, right? You wanted to see curve number. Initial value was 80, but optimized was 35. Lag time was 400. Minimum was initial value was 400. Optimized value came out to be 499. Okay, so likewise, you can just change your values and optimize the get the optimized. So I just did for only 3 subbasins and these few parameters. But likewise, you can change, you can add the elements here, you can add the parameters here, and you can optimize also so that your data or your output will be better. Okay, the objective of how this function was varied with respect to iterations, it will show. Ultimately, objective function value means RMSE value was ended up around maybe 750. So in discharge, like in these cases, in discharge cases, in hydrologic model, RMSE nearby 500 is a really good value because discharge varies in like thousands, right? Lakhs of, sometimes 10,000s of cubic, thousands of cubic. Again, that maximum value you are getting 700 cubic is also not a bad result. Parameter one, you can see how it is varied with respect to iterations. So after 80 iterations, 80, 85 iterations, value became almost constant. Right? If at all, I see, and this again, still this is not yet converged. The solution is not yet converged. Converged means the after iterations, the value should not change much, right? So still this value has little scope to change because from here almost converged, but not fully converged. You see here. So this I can make it converge by giving more iterations. I can see whatever the amount of value I have given, I mean, number of iterations I have given are satisfactory, and these values are attained. See, is here, though values are converged, but still there is a scope of conversion. So if I had given 200 simulations iterations, should have came up with a good result. Okay, this parameter, see this iteration, you can see this parameter 2, like parameter 2, whatever the values will be, this parameter has changed, but again you see from after almost like 30th iteration, almost constant, means this value has got perfectly optimized, so there is no further scope of improvement in this. Likewise this one, wetting fraction, this like this is also almost converge means it is like not change. Hydraulic conductivity, this is curve number. So curve number, see, like beautifully converged. So other parameters are scope, so we can have an option to converge or not. Fine. So this is what about, this is all about HEC-RAS hydrologic modeling. Okay, these are the complete. This is what the complete analysis is. As anybody has any questions regarding this? Sir, in the latest version of HEC-RAS, GIS is also inbuilt. Here in this project, we are used GIS tool for finding basin characteristics. Is it fine to use GIS tool in HEC-RAS characteristics? Will it make any difference in simulation study? This question is asked by Bhavindra. GIS, yes, of course, it is built with GIS techniques, and of course, yes, you can use it if at all you are want to you want to couple your HEC-RAS with the GIS techniques, and that always adds an advantage to the many analysis, of course. So yeah, we can add if you are having that the latest version if it came up with, you can add. Is any limitation to use to the calibration parameters? Is any limitations to use the calibration parameters? Any measurement criteria, 80% or like that? Okay, I'm not understanding the question. When to say the calibration is done? Acha. Okay, and measurement criteria. Okay. So I understood the question. Sorry. What Manish sir want to say, Mahesh sir want to say is like when to say the calibration is done. Calibration is then completely your up to the modeler. Sometimes my model I can say good even if I'm having RMSE like around 1000 also. So now in this case it is 700. I can say 1000 also, or NSC Oscar values. I can again directly copy those outputs. Like I'll just show you. So results, I'll go to results, simulation results. 34 curve number. Okay, I'll here, and then I'll click on this summary table. Okay, so it is like outflow and observed flow. So I can just copy this. I can just select. Okay, I'll just say copy, and I'll go to Excel, and then I'll just see what is the correlation in this. How good is the correlation? So if at all I'll add the trend line, and I'll just go to more options. Then I'll just say what is the R-square value for this. So now right now R-square value for the before calibration, because I took from the summary, so it is 0.7 approximately, right? So R-square 0.7. So in the same way, I can compute the RMS and NSC also applying the formula. So I can say this is 0.7 is if it is R-square, means it's completely my opinion whether to say I'm satisfactory model or not. But in general, if you refer the research papers and everything, R-square value 0.7 is a good. RMSE value for hydrologic modeling less than 500 QMEC is good. Many other criteria. So NSC value more than 0.7 is also good. NSC value you are getting NAS coefficient you are getting 0.7. In that case also that is good. Sir, please brief about the possible application of in irrigation command area. Okay, so this of course I want to introduce that topic also here. Sir, which is more accurate, auto calibration or manual? Of course, auto calibration will be less laborious and more accurate. When accuracy, when you say there also you are changing randomly, and in auto calibration also in manual calibration, the parameter value you are assigning is just by randomly. So both the processes are equally good, but auto calibration is less laborious. That's why it is most recommended. Okay, so this HEC-HMS and what is the use in irrigation command area is most important to understand. Okay, so has I hope everyone knows the what is the use of what is the conjunctive use. Conjunctive use means and based on this based on this question only, day after tomorrow, one of the Haji Azmatullah sir from West Indies, he is going to take the presentation on the conjunctive use. Whatever the conjunctive use, they are going to take. For that, you need some certain inputs like what is surface water and what is how much is the groundwater. So in the surface water, you can compute the surface water runoff using HEC-HMS, and then you can give an input to as in total volume of water required for the total volume generated for the rainfall. That volume, whatever volume you have to give that as an input to the conjunctive model, that input you can get it from HEC-HMS. That's the first thing. And second thing is, you must have heard the recession curve techniques. Recession curve techniques for the estimation of groundwater volume. For that, you have to have hydrographs. Okay, so once if you don't have the hydrograph, using the same techniques means there's a complete procedure like 8-line procedure or algorithm. You say you apply that technique, then you will get the groundwater volume also. In that case also, this HEC-HMS is useful. So HEC-HMS is like you understand the surface volume to understand surface volume, or maybe the groundwater volume want to compute, for which we require the hydrologic response. All those inputs you can generate from HEC-HMS, and then you can proceed with the further computations. Model is auto-calibrated and is fine-tuned by manual calibration. Is right? Yeah, of course it will be okay. If you tell you auto-calibrated and then you saw earlier, I saw earlier what we observed is the lag time was around 4,000. In fact, it cannot be more than 300, 400 minutes for that particular area. So that in that sense, this is totally a wrong value, right? That's not a practical values. That's why you have to have manual intuitions of those particular values. Then only your model will be better, because this is a mathematical algorithm. They can give any optimized values which may not make sense sometimes, right? So in that case, you have to have that intuition about those values, and then only you fix those values like these. If this value is coming within this range, is the right value, or else you have to change or recalibrate or do something else so that model will be logically or practically true in case of in your study area. Sometimes your curve number end up with like 8, 9. I have seen those models where curve number will get up ends up at 12, 20 also. Those curve numbers are like not possible, right? So for us catchment like what we are seeing. So in that case, we have to have a limitation or maximum value, minimum value, and then if you define those maximum value, minimum value, others parameter, calibration values will have impact, impact in doing the calibration, and these will change and these will adjust to the discharge value. So according to discharge value. So this is how you can move on. How many parameters are used for the calibrations? So in calibrations, usually preferred as of what I have gone through and what I have done is mostly 15 parameters, 12 to 15 parameters are always good for different basin. Of course, you don't focus on particular basin, just mixture of sub basins, and the 15 different uh, parameter values are always good and preferred also. But you can use as much as possible, as much as you want. That won't affect. Okay. So hopefully that clears all your doubts on HEC-HMS. If yes, then we'll move on with the HEC-RAS. That's also a big thing. Just say yes in your chat box. I'll start the HEC-RAS 2D modeling. Okay, so I presume that everyone is understood well HEC-HMS. If anybody and something has doubt, they can like if possible to calibrate the whole basin once. Of course, you can do. As I said, you just use the complete parameter, whatever the parameters you're using, calibration in this. You go on adding the parameters. Here you can add parameters as much as you want. You can calibrate. So I'm sharing my email. You can contact me if you have any doubt. Okay, so we'll begin with the HEC-RAS 2D modeling. Okay, so I'll close this. Okay. So HEC-RAS, what I have planned is we'll go for HEC-RAS 2D. As this like time is very short for hydrodynamic modeling, we'll simply see how you can do the HEC-RAS 2D modeling. And of course, again, the same organization is going to like again giving the training opportunities, I guess, in the next month. So again, there you can study the whole HEC-RAS or HEC-HMS thoroughly, each and every aspect. So I try to rush so that you should have at least have a glance about what exactly you can do and how simply you can do it. Of course, you can include the complexity as you understand more, and just to that complexity, to make that complexity in your understandings, or maybe in simulation, or maybe in your modeling, you should have this basic knowledge, and this basic knowledge will definitely make you explore to the next heights of your modeling. So in HEC-RAS also, I'll cover how you can do the HEC-RAS modeling, what are the different approaches, and why exactly we go for 2D modeling, and what is the use of 1D modeling also. So okay. Earlier, before, like 2D, 1D, 2D models are having its own applications. Like 1D model, you want to route the discharge from one point to other point and see if that what is overtopping or not. I mean, how much it is, how much area going in it, you won't understand. But how much, if that much amount of discharge is going to release from certain point, what will be the impact at the other point? Like this spill out of the your cross sections or not, that you can understand from 1D, or you want to understand the routing simply. Okay. Sir, later please let us know the name of organization which going to conduct the same, so that we can also attend. So same organization, wherever today where you are attending, same organization going to attend. If
Hello.
So hello.
Yes, Praveen sir. Actually, the participant are actually asking some information regarding that courses.
Yeah, they are asking the questions.
Okay. Sorry, actually, I have bit.
Okay, you just
busy in another
mention.
work. Yeah.
I'll just take a 2-minute break. Until then, you just uh, mention that.
Yes.
I'll
Sure.
ask you things about it.
Can you stop sharing?
Yeah, you can share your screen, no problem.
Yeah. Yeah, all the participants, please take note and please pay attention here. Actually, I used to show this flyer at the beginning of every session. So we are what we are doing. We are offering wide range of certificate courses in different areas of plant, smart agriculture, and water management. which are starting from February 5th, 22. In fact, in, in fact, one course, certificate course, which is based on organic farming, is already offered, and its last date is today actually. And from next, the basics of geoinformatics, it will be start from 22nd February to 14 March, and the last date of application is 15th February. Next, fundamentals of UV, that will details with unmanned aerial vehicle, drones, robotics, etc. And it will start from 15 March to 4th April. The last date is 8 March. Next is post-harvest management. It is the course uh, regarding the food processing technologies and agriculture processing technologies, which will start comes from 26 April, and the last date of application is 19 April. Next, watershed hydrological models, which is the full-fledged version of this small online international training program, which we are now conducting this from 8 to 12. The full-fledged online training program will be conducted from 17 May to 6 June, and its last date is 10 May. So it is requested to all the participants, please do register and take advantages of these courses. And the last one is Google Earth Engine with Python for climate smart agriculture. It will concern from 7 June up to 27 June, and last date will be 31st May. This flyer already I have circulated in WhatsApp group. Okay, so you can go through that, and if you have any queries, then you can contact me, either me or either Engineer Mohsin Tamboi. We both are the associate working in this project, which is World Bank funded. So I request all the participants, please go through this flyer. And if you have any query regarding these courses, regarding the submission of form, fees, and structure, you can contact me directly by the cell phone, or you can mail your queries to this mail. So hope you got clear. Yeah, actually, yeah, I have posted this on WhatsApp group. So anybody have any doubt regarding this, you can raise hands or you can directly interact with me. In a certificate course of that hydrological model, we are going to cover all this, means basically two softwares, that is HMS and ArcSWAT, that will be elaborated in detail, and each by taking the case study at every week. At the end of every week, we will take one case study, and at the end of this certificate course, we are giving one project work. So it will be also helpful to those students who are going to in plant training, that is BTech agriculture engineering students, those who have it is mandatory. Yes, UG student can also take part. The BTech agriculture engineering students, those who are at in their final year, they can take part of this in these training courses. Any other questions related to these courses, you can directly ask me, or you can put your queries in chat box.
Okay,
Yeah,
so I
Praveen
hope
sir.
everyone got an idea about the program.
Yes.
So let's start with the HEC-RAS now.
Yeah.
So I'll just demonstrate how exactly you can do the HEC-RAS 2D modeling for the flow simulations. Before that, I just want to introduce the topic. Okay. So as I was saying, that 1D, 2D has different applications. 1D will be used for the flow computation. What will be the impact when you release certain amount of water, or you want to route that discharge from one point to other point. In that case, HEC-RAS 1D will be useful. Okay. but it cannot show you like how much area gonna inundate until unless you just consider that area itself in the as a cross section. Okay, so that's one thing. Second thing is HEC-RAS 2D comes up with so many advantages. You can even understand the flood inundation area. You can see the flood inundation area, how much depth going to come with certain amount of release water is released from the upstream. But what is the problem with the HEC-RAS 1D and the 2D? I'll show you with this video. Can you see here the level? This level and this level. The problem is this level now, because this is the actual channel from where the water has been released. But you see water is increasing level because this level is at this, because of this level, this cross-section level means this small tributary, there is also the same level as this main cross channel. So what is going to, what is getting accumulated in this also? This is the problem with HEC-RAS 1D model. Because if the cross section is at certain level, it will account that volume also. So if that volume is lost in this, okay, and just imagine if this amount of volume is lost in this, then it will have a severe impact or severe analytical errors, right? That's why HEC-RAS 1D will have an issue when you're simulating it, but it has its own advantage when you have the very good cross sections. But that is certainly not true many of the cases in real watershed basins or river channels. So this is actual Tapi catchment, Tapi channel where we obtain, and then when we plotted this in error, what we found in 1D modeling. So that's why 2D model comes in handy, because ultimately it has considered the complete scenario of the whole basin scenarios. So in that case, it is not, that will be not an issue. Okay, so HEC-RAS 2D, as Riker sir was explaining you, like what is the numerical simulations, how the Navier equation been solved. So that part I will not take. I'll just directly go to the how you calibrate and validate the models once if you have developed the models. Okay, how to develop models, I'll take that part. I'll take that complete demonstration. But just understand there's some theory behind what are we gonna do and how we're gonna achieve those goals. Suppose you've done the modeling, okay, then you want to see the how the model is accurate. That you can do using the computing R square value, Pearson coefficient, or root mean square error. You can plot those 1D and 2D models, and then you can show also. Okay, so this is a RAS map, a DM. I hope everyone has got the DM. So on the data what I shared, has everyone got the data? I hope everyone has downloaded also. So just say yes if at all you got the data, like as a DM. The folder name was DM. So in that there were two folders. One is the projection file. Okay. So okay, fine. So everyone, yeah, everyone has downloaded that file. So I'll just open HEC-RAS 2D. So in this, first thing what you have to do is, first you have to create a new project. Wherever you go, you first have to create a new project. First, where you want to create the project, you have to store. I hope everyone will be following me. Just say yes, you are following me or not. Or if you want to open it, I will wait for a while. Okay, everyone is following. Okay. Just once, I'll just start from beginning again. So once you open the HEC-RAS, this window will appear. Then what you have to do is say new project. This is a new project I'm going to create. Where I want to create, I'm just clicking here. Here I'll just say in my D, somewhere in D, I'm storing it. I'll just say I'm working in this folder since 2 days, so I'll create here. Okay, and then I'll just create a folder. I'll just say I'll create a folder and I'll say session model. I'll just say name is just a session model. Okay, and I'll just say okay. Now it is the new folder is created, and I'll just say session TR1 session trial model 1. Okay, so you can name as you want, so not an issue. And I'll just say okay. Now it is saying US customer units. You can change the units from here also. Go to options, units, go to metric system. You always you always try to keep the unit in metric system. So just say okay. I'll just say yes. So you can see here beta version SI units. Everyone got it? So everyone reached to this point? If at all you guys have reached to this point, then just say yes. Means creating new project and setting the units. Okay, fine. So once if you have got it, then I'll just open project. I mean RAS mapper. This window is RAS mapper. This window, okay. This window is RAS mapper. You just see the earth on some land and water is flowing on that. That is the RAS mapper. It is written also open RAS mapper. I just open the RAS mapper. Now to have the projection like once you open the RAS mapper, you have to set the projections. How you set that is the big issue whenever you do the modeling. How can you set that projections are using projection files? So I'll just show I'll demonstrate that also. I'll just say projection. I'll click on projection. I'll say set projections. Okay, then I'll just click on this project file, and then I'll come here in DM. I already stored new projection Thyssen polygon. In the morning we created Thyssen polygon, you remember? So that shape file projection I've created. I'll show you how I created. I'll say open. See, this whole projection is uploaded. I'll say apply and I'll say okay. Now the projection is set for our system, our model, like a 2D model. Everyone did that? In DM, repeat again, sir. Okay. Go to new, set projections. Okay, once if you go to the projections, then click on this option, like option, and then direct to the DM. In the DM or the folder which I have shared with you, in that there is a new projection folder. Open that projection, select that, and just say open, and just say apply, and then say okay. So that's how you set the projections. Everyone understood the projection setting? Okay. Once if you set the projection, then I will upload the my terrains. So I'll just click on terrain, and I'll just say just right click on terrain option and create new terrain. Okay. So if at all you had not set the projections, before that I will just demonstrate you how did I create that PRG file. Okay. I'll just open my ArcMap. Like how did I came to that point where like the shared file, I'll just show you. So if at all you are using ArcMap, then it like I'm showing in the ArcMap. Okay. So the people who uses ArcMap, they can follow this. So I'll just open that shape file, which I have shared also, I guess, in the last yesterday also I shared you that shape file. So I'll just open that shape file, and then I'll just open my okay. So in this, what we have to do is I'll go to search option, and then I'll say project. Then and it's if that is the if you open this, then you will see this option. You click on define projection data management tool. So okay, that once if you open this define projection data management tool, just input your Thyssen polygon or any shape file of your study area. Okay, once if you created this, then here you can define it should be under UTM projection. So projected coordinate, sorry, projected coordinate system, it should be in PCS system. So project coordinate system you click, then you come to UTM projections. In that you come to the WGS, and in that northern hemisphere, again the Tapi, wherever Tapi river you are having like zone, so that zone you have to click. So it's a 43rd zone, so that's why I clicked on, and then just say okay. So zones, which are the UTM zones, you can just Google it, UTM zones of then of your world. You will get the world map of defined with the UTM zone numbers. So likewise, you just go to the projected coordinate systems, and you can simply select on your zones, and then you just say okay. Once if you say okay, then it will create a PRJ file wherever this season polygon is stored or saved. When I say okay, so this is done. So this is locked right now. Locked because I can't use. You see the icon here. Okay, so this is locked, and just in seconds it will create a PRJ file. So define projection is over. So wherever this file is there, means where this file is, can understand from here. This is where it is stored. There, if I go watershed and season polygon, so I'll go here in the watershed. So Thesan polygon, see Thesan polygon dot PRG file. So this is a projection file. This is how you generate the projection file. So, and this is where you have to upload set projections. Then you upload it. It should come like this. Projection WGS94 ATM zone 43, whatever the geodetics, all this, everything should be there. And just say apply and just say okay. Once if you say okay, then projection is set. Then now the next step is creating a RAS terrain. Click on this new RAS terrain, then say just plus, means wherever you are stored it. So it's in my DM, and select this lower Tapi DM. Just say open, I'll just say create. If you just create your basin in the RAS mapper. I hope everyone is following. Just say yes if you're followed until now. Seems like everyone is busy in defining the terrain or not doing, just looking at it. Just say yes if you guys have followed and you have done this much of procedure. Okay. So once if you do this, then just say yes. So this will create the projection file, I mean RAS mapper. Okay, once if you have done this, then you come here on the main HEC-RAS window and then click on the geometry. So I hope everyone is following until here. If at all you guys have followed until here, just say yes. I'm looking at your chat box. So यहाँ तक सब लोग, everyone reached to this point? Okay, so some people might be able to see the RAS mapper, whatever the image we have uploaded here, but even I'm not able to see. In that case, you have to click on this window, locate boundary conditions, and say close. Now it is appeared. Sometimes it don't appear on the screen, so you just have to go to here, select layer to view the background. So just click on that and just say okay. You will see this. Okay, fine. So everyone is able to see that. Now I'll create. See, in the 2D modeling, this is like numerical simulation, right? It's a numerical solution. So you are, whatever we are solving numerical equations, right? So in that case, we have to have a mesh for the computation of the flow over the area what we are desiring, right? In that case, we have to create a mesh. Means we have to create the flow domain. So to create the flow domain, I'll click on 2D flow area. Then I'll just zoom on to the cross section of the river. That's most important. I'll zoom to the cross section area. It's kind of slow. Okay, and then I'll start tracing my area. So this should be exactly perpendicular to your cross section. So wherever the line I'm drawing, that should be exactly perpendicular to your cross sectional area of the river. So I'll just create a small 2 points, close 2 points where I'm able to see that which is exactly perpendicular cross sections. Then I'll just simply trace. See, in the beginning, the upper boundary condition when you define, there wouldn't be that much flow, so I can go very close simulations within close flow area. Likewise, I can trace. Okay, I'm getting so many questions, but I'll just complete this process. Okay, I'll just follow this one. Okay, then I'll come here. I'll just see here. I'll come this one also. This is where I'm going to define a lower boundary condition. That's why I'll be very close and very perpendicular to this cross section. Okay, then I'll just say yes. Then I'll just follow this. I mean, this is my where the flow area going to come. And then I'll say 2D flow area. And I'll just say okay. So everyone followed until now, until here. I hope everyone has followed until this point. If yes, then just say yes in your chat box. Sir, any idea from the where we can get the good quality of DM data? Mostly Bhuvan DM river cross section not good. Look good. Yeah, like there are so many nowadays products available. DM is also there. Then again, nowadays the people are giving in the DMs giving the different file form. Of course, quality of DM. I will share you the links from where you can download. So I got only Sony Dikshit's reply saying yes. Until now, everyone followed until this point. Just let me know. Just say yes if you're done until now. We will complete within short time. This modeling will not take much time. Just say yes quickly. If you haven't followed, then I will repeat the procedure. No issues. But yes, of course, you can create DM data and you can. Yes, somebody wants me to repeat this. So once if I come here, once if I open the geometric data, from where I open the geometric database, I'll just come here. I'll just click on this one. So this window will appear. This window will appear. Once if this window appears, sometimes it will look blank. So click on this and just say okay. So it will appear. It will show you the entire this screen. Now just click on 2D area and then trace along your river having certain excess area so that it will be it will catch the flood inundation also. Okay, so this is a flow domain. Okay, once it is flow domain, see that at least at the 2 points where the where this cross section, where this flow domain is crossing to the river, it should be perpendicular. So here also I shown this point I made perpendicularly perpendicular, and here downstream. So wherever at the 2 point where it crosses, it should be at least perpendicular to the river cross sections. So that is what's requirement. Okay, once if that is done, when we'll go on to the, we'll move on to the boundary condition definition. So SA 2D area area boundary condition lines. I'll click on this and I'll just say I'll zoom because that's very much important. Okay. This should not be on the line, but it should be very close to the this line what you have drawn. Okay, it's not outside but not inside. It's very close to, not too far, not inside. It should be very close. The boundary line what we're gonna draw is just a straight line what we're gonna draw. It should be very close to the your. And can you see? I may not be able to see that how close I'm drawing, but this should be very close. Okay, so if that is done, then it is upstream boundary condition. Upstream boundary condition. And I'll just say okay. So can you see now? Though I was having little distance, but it is now exactly on the cross section. Now I'll zoom this. Then I will say the lower boundary conditions. So downstream boundary, I will just draw a line, not on this line, but very close to that line. Here from here. So that is downstream boundary condition. And I'll just say okay. Then next I'll say edit flow area. Then once if you do this, you just click on this and just say edit flow area. Once you right click on this area, you just say edit flow area. Then you just say generate computational grids. See, this is a dx and dy. What is the meshing size you want to keep? That you should put the values here. So I'll just say, I simply cannot say like this is just cake is 300, 400, 500, not like that. So you must compute it based on the current number. Okay, current number means the time and the time you must delta v upon delta x should be less than or 1. That like that it should be there. The spacing should be less than 1. That's how you have to satisfy the current number. But the problem here is like once if you once you try to satisfy the current number may result in so many grids also. So in that case, what you have to do is like you have to do this some trial and error, and you have to come to the optimal size of the machine. Generally, what is observed in this case is generally now you just if you for your demonstration, I'm keeping 300 because our simulation will get over within short time, but accuracy will be compromised for sure. But we have to come to the dx and dy values based on current numbers. So you generally it comes around 80 to 120, somewhere around it comes like that based on the flow. If you assume at 3 meter per second, something like that. So if you assume 3 meter per second, so in that basis you can you will arrive to this point. So I'll say generate 2D. So it is generated 10844 cells. Okay. Once if you have said this much cell, and then I will just say okay. Now it is generated the machines and done. Everything is done. So this is all the part of geometry. Everyone has done, I believe. So let me know if somebody has not followed. How to draw line on map. How to draw line on map. Why you want to draw a line on Acha? That land, like that question what you're asking is like how to draw this flow domain, right? If that is the case, then okay. If that is the question, then you just see select click on SA 2D area. No, sorry, 2D flow areas. Just click on 2D flow area and then just follow the procedure what I followed. So you will able to create this flow domain. Once if this is done, then come back to the RAS mapper. Now before that, you just have to say yes, save. file, I'll just say save geometry data. I'll just say geo1 data, and I'll just say okay. Now I have saved the geometry data. Everyone say how to draw. Okay, so also understood. Everyone reached to this point. Has everyone saved the shapefile? Sorry, your geometry. Just say yes if at all you have saved your geometry. I'm going very slow. I hope you should understand. Sir, what is meant by dx dy in 2D flow area dialog box? Dx dy means this, the size, when you see this meshing, so this is dx and this is dy. Okay, so this is what we are referring for, dx and dy. This should be, so see what is happening here. I'll explain you. From this point to this point, water is traveling. Okay, so suppose if your dx is so bigger, like from here, suppose you given dx as 400 meters, like this, from here to here. For a given time computation, if water doesn't reach from this point to this point, and your grid has again far ahead, in that case, you will not converge to the solution. Your solution get diverged, means you will not come to the a stable solution, means your numerical solution will not have the proper solution. It will have a lot of error in that. That's why the finer the mesh is, the finer good is the result. That is there, but finer the mesh is, the computation time is also more. That's why you have to optimize using Courant number. So what Courant number says is that based on the velocity by time, and what velocity d is equal to what? D is equals to v by t. So if you assume velocity 3 meters per second, and the time if you take consider, like you will come put the simulation time is around 130 minutes or 20 minutes, like that. I mean, sometimes it's usually generally it is like 0.1 also. Sometimes if you go for very accurate analysis, you go for 0.1 minutes. Like that's too so fine simulation you have to do. So in both the cases, you should be your dx and dy should be such that the water should reach before the time what you have given. The t means you have to define the t before afterwards. After some time, I will explain what t you have to define. That t, whatever t you are given, the water should have been reached here. If not reached, means you will diverge your solution, and the solution will have a lot of errors in that. So that is the concept of the dx and dy, and that's what the concept of meshing is. So because this is a large area, 200 300 meter area is the area, the 200 300 dx and dy is too high. Generally it is not that much. For demonstration I am doing, you refer some good research papers, you will understand like how it can give. But in general, we follow the Courant number, and then we define that how much should be the dx and dy. So generally it comes around 80 to 120. Okay, once if you have done this, then I'll just say file and just say save geometry data. Once if it is saved, come to the RAS mapper. So you go to the geometrics, then come to the open the geo 1D data. Then click on the flow 2D area, and then click just checkbox everything. Then just say complete 2D flow area. So we have got an error saying there is some issue with the loading issues there. So what you'll do, I'll just edit. Once you edit, it will just correct everything. Once if you do, come back here, stop edit, say yes, and just say again complete 2D flow area. So yes, of course, I'll tell you the means that n Manning's n value. I haven't defined that because Manning's n value will have the lot of importance in your analysis. Where right now I kept default value 0.06. The good question. So I'll explain you how to define that. There are two ways you can define the Manning's n values. One is like you can import directly the this thing, what directly the LULC image in the RAS mapper. For every classes, you can give the n values. That's the first thing. Or second thing, you let it be the at default value. Let the whatever the default value, we can calibrate that n value, because calibration parameter in HEC-RAS is only this one. only n value, because dx and dy are almost fixed now. So calibration parameter is only one. So that's why you don't like, you can calibrate that n value and then you can come to the optimum value of n values. Okay, so n value is you can import directly that procedure, like that detailed procedure. I'm not showing you right now. If anybody wants, then I'll explain later on. Right now, just focus on what we're doing. The two way we can do. One is optimize the n values, or also you can create some polygons here. You can create the polygons like this, and you can define for this polygon, this is the n value. For this polygon, likewise, you can divide the whole area, and you can define the different n values. Okay, so likewise, you can define that way also. Our second thing is, right now we are by default value 0.06 we are given. So later on we can calibrate that value and then we can define one more time. Okay. So, okay, once if that is done, once if this flow area is updated, means the compute 2D flow area table is done in the HEC-RAS mapper. Okay, what we did first, we edited a whole basin in the geometry data. We given the boundary conditions, and then we give these two boundary conditions. Once if you have done this, then what we did, we came back to the RAS mapper, then we opened the geometries, and then we went to the 2D model, and then we right clicked on. There was some error. What we did again, we edited it, and then we say computed it. Just recompute out the meshes. We say that, and then once if recomputation was done, then again we said stop editing. I'll just say yes, and then once again I did the computation of the distance. So this everything should be completed by 4x4, and here there should not be any error. If there is any error, this message will come with some certain message. So right now there is no issues, so it is completely updated. Once if that is done, then we'll come back to here. We are doing uncertainty analysis, so I'll open the boundary conditions. So this is icon. Just say I'll click on this view edit uncertainty flow data. I'll just click on that. So can you see here downstream boundary condition, upstream boundary condition, both the boundary condition what I had defined earlier. So that is now appearing here. So I'll click on this and I'll just say downstream boundary condition. I'll just say normal depth. So usually in downstream we define normal depth, but you can define any other boundary condition if you're having the data. Right now, friction slope it is asking. So suppose if I say like 0.2, I mean actually I haven't computed the friction slope. We can compute the friction slope using the DM. So I'll just say 0.12. This is friction slope, means the slope of your slope of your the basin very close to the downstream. So I'll just say okay, and here upstream I'll just define the flow hydrograph. So flow hydrographs, like you will be having the flow hydrograph. Right now, if you are having, then you can directly say fixed timing and just say mention the date. I'll just say to first 2008. I'll just say okay. Starting with time is 00:00, and I'll say the time interval is 1 hour. You can mention different time intervals here. This is the 1 hour. But right now, I'm just demonstrating this. I'll just put random data. So I'll just say 250. Then somewhere in between like 500, 5000. Again here I'll just say 100, and I'll just interpret the missing values. When you click on for just generating random values, I did that. So you can have real data also. So you can just paste from the your Excel sheets. Once if you have done this, or else what I did is here I just put some random data, mid and the first, last, and mid, and then I said interpolate the missing values. Then it will interpolate. Okay, if at all you want, and then the energy slope of the boundary condition. I'll just say same something. So you can estimate those, right? You can estimate those values, but you can plot that graph. Okay, so this graph is coming like this, right? So like very close, the flow is towards the end. No issues. Okay, I'll just say okay. So boundary condition is also defined. I'll just save the boundary condition. I'll just say save unsteady flow data. I'll say unsteady day data, and I'll say okay. Once if it is saved, once if you save this data, then okay, once if you save this, then come here. Now, has everyone defined the boundary conditions? Just let me know. How many of you have followed until now, until here? Just say yes if you have followed until this point. Only 2 yeses I have got. Out of 150, I'm getting only 10-15 yeses. I want to know. I want everyone should say yes right now, because the HEC-RAS is very simple. No one should lag behind. So Rahul sir has said 4 S's on behalf of 3 more peoples. Okay, so I am getting a sufficient number of S's. Okay, so I'll just go and simulate now the flow. For simulation, you have to come here, compute unsteady flow analysis, then say geometric processor, unsteady flow, post processing, and floodplain mapping. Starting date is what? This one, 31st August. So I'll just say 1 September 2008. 1 September. The timing is, I'll just say 2 because I 101. Okay, I can say 01 00. Ending date should be. I have opened the boundary conditions. What I defined, I'm just looking at it. So boundary condition was like end date was 05. Sorry, September. So this is 5th September. Say okay. On 5th September, the date was 2. So time was 02 00. Okay, so once if everything is done, then I can just simply simulate. So see here, computation interval. As I was talking there, the computation interval is 1 minute. Means the whatever the velocity is coming, whatever the velocity is, the velocity the flow is coming, that will reach to the next grid within a minute. That is what the meaning is. Suppose my meshing was like 500 meters, and I am saying there's 1 minute. If the water doesn't reach within 1 minute, then what I'll get erroneous solution, right? So that's what I was talking about, the current condition. So this timing is very crucial in your HEC-RAS modeling, and that is supposed to be very much like computed with keeping in mind that meshing size, dx and dy, and the timing. These time is all very much important. For just for demonstration, I'm just keeping 1 hour only, because the simulation will take so much of time if I don't like keep 1 minute or 17 seconds. Okay, once if this is done, then I'll just say 1 hour. So hydrograph interval I'm getting at 1 hour, output interval is 1 hour, and mapping output interval is also 1 hour, and I'll just say compute. So now it is computing. Okay, so this is done. So simulation part is done. Because I just gave a 1 hour of time stepping, that's why the simulation quickly got over, or else it would have taken so much of time. Then I'll just say close. I'll just close it. I'll come to RAS mapper. Now results have been stored. I can just use the results also. So if at all I want to see the depth, so this is how the depth is coming. I can play that. with the time, see how this flow is going, like flow is happening, all this flooding is happening. You might ask, like, why this flow? Why this flow is not moving ahead? Like, why it is not ending here? I guess here there is one more kakra per weir is there. This is the, yeah, somewhere here kakra per weir is there. So that is stopping the water. That's why there is a water logging. Okay, so if at all I had considered from here, then would have completely submerged. So my discharge was so huge. Of course, I wanted to demonstrate like this. That's why this is the thing. I mean, this is the complete modeling. So now, what all things you have to observe. Now the important step goes on. How to calibrate this one? How to calibrate is, now first what you do is just say the profile lines. Just click on here profile lines and add one profile here. So I'll just draw a profile line like this. I just added. I'll just say okay. On this profile line, I will draw some time series. So I'll just say flow. So this is how the flow is happening on this. Okay. So if this is the flow, and then I have to compare with my observed flow. So as I was showing in this on my presentation. Okay, so of course you can get the stages also. You can compare the stages, or else you can get this flow. So you can compare the flow, or else, because already have the input, you already have the input boundary condition. So I'll just open that flow hydrograph. Okay. So this is a flow hydrograph, right? So 364, something like this. This is the flow hydrograph. Against that, this is the output. So I have to compare, like wherever my gauging station is there. So just to demonstrate you, like if you do the proper modeling, what exactly you get? The same area only. I'm showing you the, okay. I guess the link media is not there. Okay. Anyways, no issues. So RAS map plotter. So has everyone reached to this point? Let me know if it all. Kindly share the today's PPT in WhatsApp group, because it's tutorial which helps us in the future. Okay, surely I will help. Okay, everyone reached to this point. Then I'll show you how to calibrate this model. Just say yes if at all you guys have reached to this point. This part covers like 90% of your analysis. I'll just take 10 more minutes to show you how to do the calibration. So Agrawal sir, kindly share the today's PPT. Surely I'll share the PPT. But everyone followed it. Everyone able to successfully run this model. Of course, there is an error, but that's okay. That you can eliminate by your own experiences. You do the modeling, then you will understand like what all things you can incorporate. I'll just show you how to recalibrate the model, because calibration is too poor, right? The simulation is like too poor here. You can clearly see. So how can you calibrate that one? I'll demonstrate that. Okay, come to the just across and just close everything. So I'll just say okay. Just this is the okay. Okay. Photograph. So it's like okay. Okay. The main target is here. Now we want to recalibrate this, right? So in that case, you come here, open the geometrics. Fine. Once you create, you can edit the flow area. Now you can see default Manning says 0.06. But if at all I had given land LULC map, then I would have defined the particular classes what is the n value, but I haven't given the input. That is fine. So now what I will do is I'll just say 0.038 for this basin. The value is 0.038. So there is a we have calibrated it, so the value is 0.038. So I'll just say okay. Once if you change the change your n value, again you have to come back to the RAS mapper. Again you have to compute here flow this area, because you updated the geometry, right? N value updated. So again you have to come in, you have to, if this is done, once if you do the once you again you updated your values, then again you have to simulate. Again you come here, you will change the n value, and again I will simulate the same, say compute. And the main problem was we have defined the simulation period is in hours, right? So that's also a big issue in this modeling, right? Right now it is a compression until 1 hour. If at all I make around 5 minutes, your simulation will be much better again, right? But for that n value, once you simulate, again come back here in the RAS mapper. Again you see the profile and plot the flow. So again you compare with your actual observed values. Suppose you here also you're having this thing, you can export that. So you compare with your observed values. The moment when it matches to your actual observed values, then you can say that is we have calibrated. So likewise you have to do the trial and error, and then you have to define that, you have to rectify that error. Suppose I'm just want to demonstrate you with this one more data and steady flow. Sorry. Okay. This is 1 hour, right? This is the big issue, because this is the main root for causing the erroneous results. But if I put 5 minutes, like seconds will be 2 more. If I put 5 minutes, it will take 10 to 15 minutes, I guess, for this area. I don't know, it will take so much time also. But if you compute, then you will have the actual simulation, like the beautiful simulation, not with the erroneous simulations. So likewise, you can modify your values, and you can calibrate your HEC-RAS simulations. So of course, this time is not sufficient enough to even, if I open how to import the LULC maps and the assigning any of different values in different zones. So that is today's presentation scope out of the scope. So I'm not demonstrating that part. So this is simply how you do the HEC-RAS simulations. So if anybody has the questions in this, yes, sir. So if anybody has any questions. So if I say compute here, it will take, I'll just put for compute. So it should finish we'll see how long it will take. It's going faster, so it will not take much time. So likewise, you can also try anyone a voluntary would like to extend a vote of thanks to anyone. I was just reading actually I was reading the text message.
Yeah, so it is for participants.
Yeah, I got it. So if everyone is kept for simulations, later on you can visualize the result, like the flow which was coming earlier, full of the flow domain, that will not happen. That will mostly water will flow within the your cross sections. Okay, this is done. You'll see what change has been done. Last mapper. Results depth. Okay, now we will see what is the change. Can you see the change right now? See, the water is flowing within the within your channel, right? See, now water is flowing within the channels. So this is how you can actually rectify your errors, right? So the moment when it happens, see, now the water is flowing within your channels. Earlier it was going out. Why? Because the computation time was so huge. So the water was like, I mean, it is completely erroneous time. That's why the water was flowing out. So now you can see completely water is flowing within the channel. Okay, so now like this. So in this, suppose if I again plot here, plot times is flow. If I plot, so this flow what is like this. So you might have known, like I had given the interpolations, straight interpolations, right? So now it is giving very close to the observed values because it was linear interpolation. So I was expecting the straight line here and the like this. So now it is nearly matching, right? So likewise, you can change the n values and you can have your simple simulation. So again, I'll demonstrate, like I'll just show you how it is flow is happening. This flow is started. So what is flowing within your river? Accumulating here. If there is a sea, it's downstream. In the downstream, it is not accumulated. So now this is like somewhat perfect. I won't say this is 100% perfect. So with this, I'll just say I'll wind up my presentation. Thank you.
Hello, Praveen sir. Hello. Hello. Hello.
Yes, sir.
Am I
Yes, sir.
audible? Am I audible? Hello, your voice is not clear, sir.
Yes, sir. Yes.
Yes, yes. Okay. Yeah. Oh, yeah. Thank you so much, sir, on behalf of Center for
Mine.
Advanced Agriculture. Yeah, yeah. Hello. Hello. Hello.
Hello.
Yeah.
Ah,
Am I
yes.
am I
Yes, sir.
audible?
Yes, sir.
Yeah, yeah. Yeah. Thank you so much, sir, on behalf of Center for
Yes, sir.
Advanced
Yes, you are
Agriculture.
audible.
Yeah, on behalf of Center for Advanced Agriculture Science and Technology on Climate Smart Agriculture and Water Management, Mahatma Krishi Vidyapith Rauri. Myself, Engineer Kalpesh, Research Associate WRM. I heartily thank you on behalf of my institute and all the participants to be presented your HEC-HMS modeling and HEC-RAS modeling very nice way that it would understood very well to the all the participants. Actually, I request any participant to extend a vote of thanks to our today's speaker. So kindly raise your hands if you voluntarily want to extend the vote of thanks to our today's speaker. Yeah, Rahul Agrawal. Yes. Yeah, Mr. Rahul. Yes, you can speak.
Thank you, sir. Thank you for the wonderful session, both in HEC-HMS and HEC-RAS. The things were properly explained, and we will try it at our end. And number of things can be incorporated. Thank you for such a wonderful session. Thank you, Praveen, sir. I am Rahul Agrawal from MIT Aurangabad.
Yeah,
Thank you, sir.
Thank you, Rahul.
yeah, thank you, Rahul, for your kind words towards our speaker. Yeah. Okay. Yeah, thank you so much once again for joining all the participants. Thank you, Praveen sir, once again.
Thank you very much for
Yeah.
inviting me for this wonderful lecture.
Yeah.
I hope everyone has understood the things what I tried to cover. Of course, it was in short durations. In 2 hours, I had to demonstrate whole complete HMS because it was not so that easy. An idea about what can be done. Has some other queries, further queries, they can contact me through the mail.
Yes,
I'll
yes.
happy to help you
Yeah,
out.
and this
So,
course material, whatever
again,
the presentations has been given by experts, yeah, we from organization team will be sharing this, all the presentations and course material in a WhatsApp group. And finally, we are also going to prepare one training manual in which all the lecture notes will be made available after this training program. Thank you one again. Thank you one and all for joining. Thank you, sir.
uh,
Yeah, yeah. I'm ending
okay,
meeting.
sir. Thank you.
Yeah.